Hello everyone, welcome to the channel Statistica Hub. So this is our lecture number 4 in the course SH201A. I hope you are able to understand the basic concepts of probability and PNC. Now we are moving to something that is like little bit advanced, we can say. So we have the concept of conditional probability and independence. So technically this topic is like not very tough. Okay, people keep up like the conditional probability to be like very like separately from the general probability concept, but I will take up like this part as a like very basic simple probability, but with slight change. Okay, so let's see what is the meaning of conditional probability. So we have conditional probability. So as the name says, this is some sort of probability that is holding some kind of condition. Okay, so let's say you are having some event A, some event B. Now, if I say you have to calculate probability of event A given that B has occurred. So the meaning for this one is find the probability of occurrence of A given that B has already occurred. B has already occurred. So this concept is like very simple. So I feel that the students knows the basic probability. So for the rule for this one, that will be simply, this is denoted like the probability of A given B. That comes up like probability of A and B divided by probability of event B. Okay, that is the meaning of like the conditional probability. Now we will understand like how this is coming up. So before moving to this particular formula, I will go for the standard form. If I say you have to find probability of any event A. So how do you find this particular probability? So you write this as number of elements that is common in A divided by number of elements that are total in the sample space. Correct? The basic probability form, number of elements favorable for the event A divided by total number of elements in the sample space. Okay. Now, if I say this is my particular sample space that we are dealing with, okay, A is the event that is occurring at this place. So can you think about like what is the number of elements that are common in A and the sample space S? That will be simply number of elements that are in A, because that is only the common part in both of them. So I can just simply write this part to be number of elements in A and S divided by number of elements in the sample space. Okay, play a little bit more. So if I divide the numerator by number of elements in the sample space, and if I divide by N of S in the denominator also, so I will be finding probability of A and S divided by probability of S. So we can see like this formula that is simply coming up to be similar to this one. So what is happening in these two different setups? So you can see I'm finding the probability of any event A, that is coming up like probability of event A given that the sample space has already occurred. That makes sense. So you can write any probability of any certain event or any particular event A that is coming out to be probability of A given S. That makes sense also, because we are going to calculate probability only if there is some sort of sample space, because we have considered in the last chapter or in the last slides that there is something SBP, the probability space. So you need to have the S, you need to have the B, then only you can define the probability function. So we can see once we are having the sample space, then we are able to define the respective probability. So moving with the same concept, I am getting probability of any event A, that is probability of A given S. So we can see this is nothing. If you say probability of A given B, that means to say in this setup, we are defining that we have to find the probability of event A given that you are given some sample space. Now, in this setup, you are not given the sample space, you are given the event B, that is your new sample space. Like this is another way in which we can see this particular probability. So what is happening? If you make the Venn diagram, you'll be getting the sample space, you'll be getting some event A, you'll be getting some event B. Now you are saying that B has already occurred. Now tell me the probability of occurrence of A. So under this sample space, this was the old sample space. You can say this is the new sample space. Under this sample space, what is the probability of occurrence of A? So that will be this part divided by the total. That is the given condition. So we are just simply getting the same thing. So if you just expand, if I go back to this formula, I'm getting number of elements in A and B over number of elements in S over number of elements in B over number of elements in S. Being a positive number, this can be cancelled out, and we are going to get number of elements in A and B over number of elements in B. So you can see this is nothing if you compare with this particular part. I'm simply getting this particular probability to be the conditional probability. Okay, and this formula holds true only if we are having probability of B greater than 0. And surely in these kind of problems, the probability of B will be 0, greater than 0. It will not be equal to 0. Now someone can think, sir, why this can't be 0? So this can't be 0 because we are given the condition that B has already occurred. So if B has already occurred, that means to say it must be having some sort of probability. This is a possible event, so you can't have the probability to be 0. So that is the concept of conditional probability in a very simple, very basic form. Okay, moving ahead. Okay, we are given some example now. So we are having an example. What is the probability of drawing an ace from a deck of cards, given that the card name is spade? So you have to find probability of getting an ace, given that you are having some spade. So simple formula, probability of ace and spade divided by probability of spade. Okay, so that will be coming out like common ace and spade, that will be only 1. So 1 over 52 over 13 over 52. So I will be getting 1 over 13. So that is the concept of conditional probability. Very simple format, probability of any event A given that some other event B that has already occurred. Okay, I hope that makes sense. This is a very simple form. Okay, moving ahead. Okay, now we are having, okay, there is another example. So, okay, I have to tell one concept at this place. So we'll be dealing with something that is known as multiplicative rule. Multiplicative rule. Okay, so what is the meaning of like multiplicative rule? Okay, so in this particular part, I will say that you have to calculate probability of any event A and B. So what will be this probability? So let's try to play with some dummy example. Let's say I'm having this example that if I say that in the breakfast, I had bread and milk. So what does that mean? Like, how did I had this bread and milk like simultaneously? Just think about this case, like being a decent human person, not like someone like, okay, eat anything. So assume that like, okay, I'm a decent person and I like smoothly, finally. So I will be having this kind of structure. Maybe I'm having like one slice of bread. I take one bite. Just after that, I'm having the milk maybe. Or the other case can be there. I'm having the milk. Then after the milk, I'm having the bread. So this kind of setup is there. So if someone says that there is some simultaneous occurrence, so technically that is never a simultaneous occurrence. That is something like this, that event A that had just occurred, and after the occurrence of event A, without any gap, the other event happened. That is the case. So in this setup, I can have the condition that if I say I am having bread and milk, so that can be like this, probability of bread into probability of milk given that I already had the bread. This is like one way. Or the other way can be like this. Maybe I'm having the milk first. So probability of milk into probability of taking the bread given that I already had the milk. Okay. And I have written the word or. That is a very important topic or very important concept. Like you can't say that both the things can happen simultaneously. So that is not possible. Either you can have the bread first or you can have the milk first. Then only you are going to apply the conditional probability. And this kind of rule is known as multiplicative rule. So for this particular probability, you can simply write this can be written in two forms. It can be probability of A into probability of B given A, or we can have probability of B into probability of A given B. Under this condition, you can simply write probability of A greater than 0. At this place, you can write probability of B greater than 0. So that is the condition of, or we can say that is the particular rule, the multiplicative rule, how we can play with the concept of probability of A and B using the conditional probabilities. Okay, I hope that makes sense. Now, now someone say, okay, sir, this is fine. Like we are having two events, but what if we are having like more than two events? So if you just consider that you are having three events, then what will happen in that case? So you will say probability of A1 intersection A2 intersection A3. So again, the concept just goes same. You can have multiple cases. But in this concept, if I just start with A1, that first I had the A1, then I'm having the A2, given that A1 is already there. Then I'm having probability of A3, given that A1 and A2 has occurred, and so on. You can have like multiple cases. You can go for the generalization case in this case. Okay, so that's how you calculate the multiplicative probability, and that's the concept of different cases that we can make up under the concept of multiplicative rule. Okay, let's move to the example. The example says that in a survey of 60% of the people, they like coffee. Okay, you are having 40% of coffee drinkers that also like tea. Okay, so very simple concept. You are given probability that a person is taking coffee, that is coming out to be 0.6. And you are given probability of tea, given that a person is like a coffee lover, that is coming out to be 0.4. Now, what they want you to calculate probability that a randomly chosen person likes both coffee and tea. So we need to calculate probability of coffee and tea. So that will be simply, so in this setup, you can say, first we are having the coffee event, then we are having the tea event, given that the coffee event has already occurred. So probability of C into probability of T given C. So that is coming out to be 0.6 into 0.4. We are getting 0.24. So that's the concept of multiplicative rule. Okay, and this was like one example, a very basic, very simple example. I hope you are able to understand. Okay, moving ahead. Now we are having the concept of independence. So let's try to test that part also. Okay, now if someone say that one event that is independent of the other event, so what does that mean? Like without solving anything, if you just think about this case. So if I say event A and B, we have to check for the independence. Okay, so if you just consider that we are having probability of A given B. So if the occurrence of other event that is not affecting the other event, like I'm using other, so you can simply say the occurrence of one event does not affect the occurrence of the other event. In that case, we call these two events to be independent events. So in that particular concept, I can simply write if occurrence of one event does not affect the occurrence of other event, then they are independent events. Okay, simple concept. So in this case, if you say probability of A given B, that will be simply coming out to be probability of A. Because like the A event that is not affected by the event B. So we are not concerned whether the B has occurred or not. So if you just expand this form, so I'll be getting probability of A and B over probability of B, that is coming out to be probability of A. So you can simply write this part to be probability of A and B, that is coming out to be probability of A into probability of B. So that is the concept where we can say the events are independent. Okay, so two events are independent if and only if this condition, if I just say condition number one, if this condition is being held, then you call these two events to be independent. And this particular probability that we have written, that in taking into consideration like more than or equal to two events, these type of probabilities are known as joint probability. And a probability that is taking up only like one event, these are known as marginal probabilities. Marginal probabilities. Okay, we are going to make use of this concept like again and again. We are go for like higher statistics, then we are going to deal with like IID random variables. So likelihood function and all those things, like we have to consider that we are having the independent probability or the independent condition that is being held. So you will be able to write the joint distribution to be in this form, the multiplication of the marginal one. Okay, so that is like one concept about the independent events. Okay, now think about one case. Is an event independent of itself? Just try to think about this problem. This is very, very simple. You'll be able to solve. Okay, let's come to the example that is given over there. So the example says that are the events rolling a 4 on the first dice and rolling an even number on the second dice independent? Technically, you are having two dice. Okay, so the event A that is saying 4 on the first dice. Okay, so first dice that is showing 4. That is your event A. The event B that is saying the second dice is having even number. Okay, so first we will try to check out their marginal probability. So if I go for the marginal probability for this one, getting a 4 on the first dice. So what will be the probability? There will be 1/6. Okay, getting a 6. So for this one, the probability, if I just say probability of A, that is 1/6, probability of B, that will be coming out to be 3/6. I'm getting 1/2. Okay, now you have to check. We have to go for the independence. So just check the joint distribution. So probability of event A and B. So they are saying you are getting 4 on the first dice and some even number on the second dice. So how many cases will be there? So just check out the cases. So if I just go for checking out the cases, so just make the concept like 4, then you can have 2. Okay, 4, you can have 6. 4, you can have 4. So we are having like 3 cases, correct? So I will be getting like 3 cases over 36. The total we are having, that is 36. Okay, just check out whether I miss out something or not. So we are having 4 on the first dice and some even number on the second dice. So 4, 6, 4, 2, and 4, 4, correct. So this is coming out to be 3/36. That is 1/12. Correct? Now we have to check whether these are independent or not. So just cross check probability of A into probability of B. So that is coming out to be 1/6 into 1/2. I'm getting 1/12. So you can see this condition that is being held. So we are getting probability of A intersection B. That is coming out to be probability of A into probability of B. So you will conclude that the events are independent. Okay, so that's how we can apply the independence condition rule. Okay, I hope this concept was easy. You're able to understand how did we approach this particular concept. Okay, moving ahead. Okay, then there is like one more problem. Like this will be the last problem in this particular lecture. And we are having some scenario. A system has 2 components, each with a reliability of 0.9. Okay. The system works if at least one component works. Okay. So we are given 2 components. Let's say the component A, we are given component B. And the system works if at least one of them is working. So we need to calculate probability of A union B. At least one, correct? So either A, B, or both of them. So we have to calculate this particular probability. Okay. So what will be the probability if both the system will failing like only in this one condition? So you can simply see the system will fail if both the components fail. Okay, so when the both components will be failing, so that will be simply probability that A is not working and B is also not working. Okay, and we can see these 2 components, they are working like independently from each other. So that will be coming out to be probability of A complement into probability of B complement. The reliability that is given 0.9. So this will be coming out to be 1 minus 0.9 into 1 minus 0.9. Okay, so I will be getting 0.1 into 0.1, 0.01. Okay, so this is the probability where the system is not working. So the system will be working, that will be 1 minus probability system not working. Okay, so in this particular concept, that will be coming out to be 1 minus 0.01. I will be getting 0.99. So that is the probability that this particular system that will be working on. Okay, one more concept that you can take into consideration, like if you find like you are having some event A, some event B, so you can have different combinations. So you can have some combination like A, B. You can have some combination A, B complement. You can have the combination A complement B, and finally you can have A complement B complement. So just remember that if any one pair, if any one pair is independent, then the other pairs, then the other pairs will also be independent. Okay, just remember this concept. So you don't have to check for the other pairs. If one of the condition or one of the pair that is holding up the independence condition or the independence rule, then all the other pairs, they will also be independent. That means to say, if this is independent from this, then this will also be independent. They will also be independent. They will also be independent. So if any of the pair that is holding, just apply the same rule on the other three different pairs also. So that is the concept of independent events. So in this lecture, we covered the independent events, we covered the multiplicative rule, and we covered the concept of conditional probability. I hope you are able to understand the concepts of like the conditional probability and the independence. That's all in this particular lecture. Bye. Thank you.